so a sequence is a list of numbers with a definite order. That's your base definition. So it has an order, like a sequence of events. So one thing to notice is that for every positive integer n, we call n the index, there's a corresponding number an. So a sequence is a function, right? However, it's not a continuous function. In fact, it's discontinuous at every point because it would just be over the integers. So you would have like 1 at 1, 2, 3, 4, and so on. So it's discontinuous everywhere, right? And so because it's kind of a weird function that's discontinuous everywhere, we usually just write the function in terms of a sub n instead of f sub n, because functions f sub n or f sub n, f of n, we generally think of to be continuous in most places, right? Those are like the functions that we do calculus with, and to be able to do calculus with a function, you kind of have to have the function be continuous in most places. All right, so let's look at some examples of sequences. Oh, a couple of just notation notes. Generally, we'll write sequences inside of braces or curly brackets. And so when you want to indicate like a sequential function, you could write it curly brackets an, or you could write the actual function that it is. So I could go, okay, this is the function n over n plus 1. And that's understood to be start with 1, plug in n, and you would get 1/2. Plug in 2, 2/3. Plug in 3, 3/4, and so on, right? Unless otherwise indicated by this sort of notation. Sorry for the blurriness of these. I don't know what's going on. It's understood that your first term will be found by plugging in 1 for n. If you want to start with a different value for your first term, you could by just putting like n equals 2 here or whatever it is. And we'll once in a while see something like that. Can you see from there? Okay. So far, so good? Oh, yo, you're going to do this to me, Apple Pencil? All right, so here are a couple examples of just some sequences. And so I've put the formula in braces. Just a couple things to note. Here we're starting at n equals 1, going to infinity. If you don't put n equals 1, it's understood that it starts at n equals 1 and goes to infinity. However, if you want to start it someplace else, like this one starts at n equals 3, you can indicate that using that sort of notation. So that would be 0, 1, root 2, root 3, and so on. Yeah, an integer. Yes, a whole number. Yes. B, notice that this -1 to the n out front is going to cause the sequence to alternate its sign, right? So you have your first term is negative because you have an odd power for n. Second term will be positive, third term negative, and so on. So that's a series of interest, or a sequence of interest that we will be exploring. And then that last one, that cosine, is also a sequence that will eventually alternate, not necessarily every other term, but we know that cosine is a wave function, right? So you know that the points are going to be kind of traveling along the wave of that function, and it could be either a dampening function or a function, like a dampening function is something that goes like this, like the way sound travels, it dissipates over the distance, and the amplitude of the sound becomes less and less as the wave travels out. Or it could be an expanding function, which would just be the opposite, right? And that one is neither. That's just a regular cosine function, but it has a little adjustment to its period, so it's going to oscillate a little faster than normal. But it's still, the points are just going to follow the cosine wave like that. Perfect. Perfectly graphed. It's like I am Desmos. All right. But then there are some sequences that don't have a simple defining equation. So I could do like A, the sequence P sub n, where P sub n is the population of the world as of January 1st in the year n. So generally that sequence is probably increasing, but I can't just, there's not a formula that's going to define that super easily, right? Or if we let a sub n be the digit in the nth decimal place of the number e being Euler's number, which is like 2.72, but it's also an irrational number, right? Like pi. And so if I let a sub n be the digit in the nth decimal place, there's no formula for this, but I can start it off 71828182845. And then I'm sure you've heard of the Fibonacci sequence. Maybe heard the name. So that's what we call a recursively defined sequence. And you can define that pretty well, but you just have to use the first few terms. So Fibonacci sequence is defined such that f sub 1 is 1, f sub 2 is 1, and then every f sub n after that is defined as the sum of the previous two terms. So specifically, n has to be greater than or equal to 3. So it starts off 1, 1, and then to get the next term, you add the previous. So to get a3, I add 1 plus 1. That gives me 2. To get a4, I add 2 plus 1. That gives me 3. To get a5, I add 3 plus 2, 5. And then 5 plus 3, 8. And then 8 plus 5, 13. 13 plus 8, 21. So then what would the next term be? 34. Then 55. Et cetera, et cetera. This is closely linked to something called the golden spiral. And the rule of thirds in photography, and maybe we'll go over that. Maybe Friday we'll talk about that a little bit, how the Fibonacci sequence relates to those things. It's kind of cool. It's like pop math or whatever, you know, like something you would see like a Vox video about, but it's kind of cool. All right. See if my Apple Pencil is charged here. All right, so let's talk about limits of sequences. So sequences such as the one in example 1a, which was defined as a sub n equals n over n plus 1, can be pictured by plotting its terms on a number line or by plotting its graph. So this one is visualizing, this one on the right, figure 2, is visualizing the sequence as a function. And then this one is a number line diagram of the sequence. So all we're doing is plotting each term on a number line. And we notice that the terms seem to be getting closer and closer to 1, right? So just like your calculator has polar mode and has parametric mode, it also has sequence mode. So let's take a minute and practice graphing that. Sequence mode is not as great, but I think it works. It's good to have some knowledge of it. I have extra calculators if anybody needs one. So now you're going to know how to use all the modes in your calculator. We're going to set it to sequential mode. Hello, Mr. Steiner. Yeah, Calc 2. Have a serious talk with him. Send an email. Don't ever interrupt my class again. Okay, so we're going to put our function here, which is n over n plus 1. I just want to try this with the one we were just looking at. See if we can reproduce this graph. Oh boy, I should have reviewed how to use the function notation. But let's see if I can figure this out. So u1 would just be our first term, which would be what? 1/2. And u2 is our second term, which is 2/3. And let's check our window. Yeah, so here you can set. I don't know why you need to define. Oh, you know what? Yes, I do. This just gives you the ability to define if your first n needs to be 1 or if it needs to be something else, right? So we saw that example where n started at 3. But for this one, I would want to start at 1. And for the window, n min and x max, so let's say I want to see the first 10 points. That's fine. And the plot step is going to be 1. All right, so now I'm going to set my window. I want my x min to be 0 to at least 10. I'll go up to 11. I don't know why my x scale is 3s. And then my y min, we saw in this graph that it's not going to ever breach 1, right? It's going to approach 1, so I really don't need to see that high. So I'm going to just set my y min I'll set to 0, and my y max I'll set to 1. And then my y scale, let's look at little y scales. So maybe, yeah, let's set it to 0.1. That's good. So now if we graph it,
We've never had a sub ever.
I'm going to just start calling it in the window E min. Our E min. All right. So good. That's how we can kind of use our calculator to help us graph a sequence. Moving on. Let's hit more basics today. So from figure 1 and 2, it appears that the terms of the sequence are approaching 1 as n become large. In fact, if I take the difference between 1 minus n plus 1, or sorry, n over n plus 1, and I'll just make sure we know why, that's n plus 1 over n plus 1 minus n over n plus 1, which is 1 over n plus 1. And then if I take the limit as n goes to infinity for this, just intuitively, it's been a while since we've dealt with infinite limits. But what's going to go on with that denominator as I let n get infinitely large? The denominator. It'll just get infinitely large. And when I have a constant over something getting infinitely large, what is the overall fraction approaching? 0. right? Because think about it this way. I've had 1/10, 1/100th, 1/1000th. These are progressively smaller numbers. The fraction is getting closer and closer to 0, right?
Yeah.
So anytime you have some constant divided by something that's getting infinitely large, the fraction itself is going to approach 0. So this is 0, which proves that basically this must also be 1, right? Because that was representing the difference in 1 minus our sequence. So we've proven that our sequence must approach 1. And so it's been a while, but I could have just directly proven that our sequence approaches 1. Let's remind you guys how to do that. This was a Calc 1 concept. One way to do that is divide by the highest power of your variable in the denominator. So if I do n over n, n over n, 1 over n, that becomes 1 over 1 plus 1 over n. We have a property of limits that says I'm allowed to take the limit of each term in an expression separately, basically. So these constants are all just going to stay constant as n goes to infinity, right? But what is this term going to approach as n goes to infinity? It goes to 0, so I'm left with 1 over 1 plus 0, or just 1, right? All right, intuitive definition of limit. A sequence an has a limit L, and we would write that as the limit of an as n approaches infinity equals L. I prefer this one. This one is nasty looking to me. I don't like it. But they mean the same thing. If we can make the terms an as close to L as we like by taking n sufficiently large. Meaning it'll never reach L, but I could go, hey, I want it to get within 0.00001 of L, and E-min could go, okay, just start at the 100th term, and it'll always be that close. And in fact, get closer. Does that make sense? And we could play that game forever. I could give any number that's as close as I want it to be to L, and you could tell me which term I would start at, and then my sequence is that close and only getting closer to L. So if the limit L exists, we say the sequence converges to L, or is convergent. If the limit does not exist, then we see the sequence diverges or is divergent. This is the rigorous definition of limit. I'm not going to test you over this, so don't feel like you have to write it down, but this is like real analysis now. And so what I gave you was an intuitive definition, but this is called an epsilon delta proof. So this says that this limit exists as n approaches infinity and equals L if for every epsilon greater than 0, there is a corresponding integer n such that if lowercase n is greater than that uppercase n, then the difference between the sequence and the limit will be less than epsilon. This is just a formal way of stating the rules of the game that I talked about that me and E-min were playing. I would say, E-min, I want the difference in my sequence and the limit to be less than this number epsilon. And then E-min would come up with a number capital N such that if we take every term after a sub capital N, my sequence will be within that distance of epsilon. Okay. All right, so a theorem. If the limit as x approaches infinity of f of x equals L, and f of n equals a sub n, where n is an integer, then the limit as n approaches infinity of the sequence is also L. All that means is if we look at the sequence, which is a bunch of discrete dots as a function, right? It's this non-continuous function here. And this hopefully will be intuitive that this would make sense. Well, if instead I go, okay, well, let's redefine this as a continuous function. So we're going to connect the dots and deal with the function that goes through all those points, but also includes all the points in between the sequence, right? So it's all of these. Cool. So if I can prove that the function will approach L as x goes to infinity, that means the sequence will approach L as n goes to infinity, because the sequence is just a subset of points on that function. Does that make sense? All right, so we're just into some technicalities here. AN is the sequence that's only defined over the whole numbers, like Tommy brought up, whereas f of x is the continuous function that also contains all those points, right? So if you can prove that f of x goes to L, then it must be true that AN also goes to L. And a big thing that we're going to be using is this, right? This was the huge idea when we deal with infinite limits, and that's just if you let n go to infinity and you have a situation where your denominator is getting infinitely large, but your numerator is staying constant, then the whole fraction will approach 0. And that goes beyond just this, n to the r, where r is greater than 0. That's just a power function. If you can just remember that intuitively, if your denominator is getting infinitely large and your numerator is staying constant, the whole fraction will eventually go to 0. All right. So the reverse of that, if we want to look at divergence, if as you let n increase to infinity, your outputs, your AN values, go to infinity, that means that for every positive number m, there's an integer n such that if my index is greater than n, then my outputs will be greater than m. All that is the reverse of the game that I was talking about with E-min. I can give as big a number as you want. I want my outputs to be bigger than 1 trillion. And then E-min can say, as long as you start at the nth term, your outputs will always be bigger than 1 trillion. And then I could say, oh, well, I want them to be bigger than 1 trillion and 1. And you'll say, well, okay, then you just need to start at the next term down the line, and they'll be bigger than 1 trillion and 1. And so that's just called divergence towards infinity. And that just means, and it could be negative infinity as well, that just means the sequence is eventually getting infinitely large positive, or if it's diverging towards negative, it's getting infinitely large negative. Sorry, that light blue doesn't read very well, does it, on the screen? And that's just in contrast to, you could have divergence like sine or cosine. I need to, hold on. Like sine or cosine. And those would be considered divergent, but they're not going off towards infinity or negative infinity. They're just not approaching anything, right? They're not getting closer and closer to anything. They're just bouncing back and forth. That's still divergent. This is just a special kind of divergence towards infinity and or negative infinity. Are we good? Are we alive out there online?
Barely.
Okay. Bunch of limit laws for sequences. They're all the same as our limit laws for functions. I don't really feel it necessary for you to write these down unless you do. This slide is available to you, so you'll always have access to it on the PDF, and your exam is going to be open note or whatever. So you can access this during that, but don't get complacent. That doesn't mean you shouldn't do the examples with me, because if you don't do that, you're not going to get practice and you're not going to remember how to do some of these. But this is just basically saying limits are really flexible, and if you're taking limits of functions that involve multiple expressions, to summarize this, you can basically take the limit of each term separately. All right. The squeeze theorem. This was one we did, I believe, last year. Yeah. So this is just the squeeze theorem for sequences. If you have three sequences, and you know that A sub n is always smaller than B sub n is always smaller than C sub n, meaning B sub n is sandwiched between the other two sequences, and you know that the outside two, so the limit of A sub n as n approaches infinity and C sub n as n is approaching infinity, those approach L, then that means the middle one must also approach L, because it's getting squeezed in between those outside two sequences. And I think we do an example of this to kind of remind you how to use this squeeze theorem. It doesn't look like a real word. Did I tell you about when in QR I tried to write vaccine and I couldn't remember how to spell it? And
You didn't tell us, but
put two X's in it, and then they were like, "Are you an idiot?" It's like, I'm used to seeing like people write vax, and I just momentarily forgot that's not. I know. Oh my God.
None of us are ever going to listen to anything you say ever again.
How do you have a degree? All right, another theorem. If the absolute value of a sequence as n approaches infinity is 0, then the sequence itself also approaches 0 as n approaches infinity. This one maybe doesn't seem that useful, but it will come in kind of handy. Yeah, there's a few here. And these are mostly theorems that are related to, this one isn't though, but they're mostly theorems that are related to the same theorems that functions have. Okay. We already did this. I'm going to skip this example. This one was 1. All right, let's do this one though. So this is a good one to kind of show why we needed that technicality that if we redefine the sequence as a continuous function and prove that the function has a limit, then the sequence will also have a limit. And so here's the reason why. When we're looking at the limit as n goes to infinity of natural log n over n, you know what, let's graph this one in our calculators real quick, just so we can see if we think that visually there's a limit. Before I do that though, what does natural log n do as we let n get infinitely large? Logarithmic functions grow. They grow very slowly. They're like the slowest growth you can have that's not asymptotic. So they do diverge, they do this, right? But it's super, super slow growth. Meaning, as you increase n, ln is also just going to increase towards infinity, but really, really slowly, okay? And then what does the denominator do as n approaches infinity? It gets larger. It goes to infinity as well, right? All right, so now let's look at our calculator and just take a look at what we think the graph of this would be. I'm just going to change this to natural log n divided by n. No, by n. So this would be natural log of 1 over 1, which is 0. This will be natural log of 2 over 2. All right, so it's increasing. I think all of this is fine. All right, so it does seem to be doing something, right? So it increases really quickly at first, but then it kind of stabilizes. Now it looks like it's decreasing, right? Well, this isn't a continuous function, right? This is what we call a discrete function. So I can't do calculus with this. Like I couldn't find its derivative because a function has to be continuous to have a derivative, right? But if I could connect these dots and look at the continuous function that connects all those dots, I could do possibly calculus with that. Why would calculus be helpful in this case? You guys remember what kind of form this is called? Infinity over infinity or 0 over 0. Those are called indeterminate forms, meaning they may have a limit or they may not. We can't tell in this form. Do you remember what rule we're allowed to use when you have an indeterminate form of infinity over infinity? Some guy's rule. It's very French sounding. I think he was actually, yeah. So we could use L'Hopital's rule, but L'Hopital's rule involves taking a derivative and doing calculus, which we can't do on a discrete function. You have to do on a continuous function. So we have to let f of x equal natural log x over x, right? Then the limit as x approaches infinity of ln x over x, we know already will be indeterminate, so we can use L'Hopital's rule. So I'll just do an equal sign with an h over it. And L'Hopital's rule just says take the derivative of the numerator, which would be what? 1 over x. Take the derivative of the denominator, which would be 1. And then reevaluate the limit. Limit as x approaches infinity of 1 over x, which would be 0. And then I'll conclude with, therefore, the limit of our function as n, or sorry, our sequence as n approaches infinity of natural log n over n has to go to 0 as well. And that theorem that said if the function goes approaches a limit, then its corresponding sequence also approaches a limit was just a numbered theorem. So I don't need you to reference it. You only need to reference theorem if they have an accepted name across all of mathematics. Like if you use the squeeze theorem, you should justify by saying by the squeeze theorem. All right, all right. All right, so evaluate the limit -1 to the n if it exists as n approaches infinity. Well, this is one, if we look at the first few terms, the first term is going to be -1. The second term is going to be +1/2. The third term is going to be -1/3. Fourth term is +1/4, and so on and so forth. So this is called an alternating sequence. Let's take a look at what that looks like. Change this to -1, -1, the n over n. First term is 1. Second term I said is -1/2. Now this is going to oscillate around the x-axis, negative, positive, so I'm going to change my window slightly. Let's go y min is -1, y max is 1. Let's do like 20 terms just so we can get a better view. I'll go 0 to 20 on x. Oops. Too many classes. There we go. So what's going on is we're bouncing, right? We're going down, then back up, then back down, back up, and so on and so forth. But does it look like it's closing in around something?
Yes.
So if you had to guess? All right, but can we prove that? Trick question, no. Moving on. I'm just kidding. Yes, we can prove that. So we had that absolute value theorem that said if the absolute value goes to 0, then the original function must also go to 0. So that's going to be helpful here, because we can say the absolute value of -1 to the n over n is just going to be 1 over n, isn't it? And we know that if the limit as n approaches infinity of 1 over n will just be 0, so then I'll say therefore the limit as n approaches infinity of -1 to the n over n is also 0. And again, it's by that theorem. That theorem isn't given a name, it's just a numbered theorem, so I don't need you to reference it. I just need you to be able to use it.
Mr. Toller,
Yes, sir.
so I have to get passports down in Wickenburg, and I have to be ready by 11, so I have to leave.
All right, well, I'll record
Early.
this and post the rest of what I do.
Okay,
All right,
all right,
Later.
thanks. See ya.
later. All right. Another one, if the limit of a sequence as n approaches infinity is L, and the function f is continuous at L, then the limit of a function of the sequence is equal to f of L. This sounds weird, but it'll make sense in the context of the next example, I believe. right. So let's look at this. If I'm looking at the limit as n goes to infinity of sine pi over n. Well, if I just focus on that input, pi over n, and I make that my sequence, an equals pi over n, and then I look at the limit as n goes to infinity of that, what would that limit be? So your numerator is just pi, that's a constant, right? What's your denominator doing? Just getting large, so what's the fraction going to approach eventually? Yeah, it's going to go to 0. And so that last theorem just said, okay, if that's the limit of my interior function or my interior sequence, and sine is continuous at that value, then the limit of this sequence will just be sine of 0. Well, sine is continuous everywhere, and sine of 0 is just 0. So easy math. All right, now we're going to discuss some discrete mathematics, which is not something we do a lot in calculus, but when you have discrete, I mean gaps between points like these sequences. And so you haven't seen much of this probably in your math careers, but you guys know what that is? What? Yeah. Yeah, it comes up a lot in probability and stuff like that. Combinatorics, so combinations, permutation stuff.
Yeah.
Yeah, well, you do a little bit of that in Algebra 2. That's called factorial.
I didn't like that part.
Algebra 2 teacher's favorite joke would just be to yell n at you and then say, no, that's not what that means. So all factorial means is that you're multiplying the whole numbers up to n. So a factorial is only defined for a whole number. So like 6, let's just do 4 factorial means 1 times 2 times 3 times 4. Does that make sense? All right, so let's explore the first few terms here, see if we can recognize a pattern and then maybe prove some convergence here. So if we talk about A1, that is 1 factorial over 1 to the 1, which is 1, right? We talk about A2, that's 2 factorial over 2 squared. That's 1, I should say 1 times 2 over 2 times 2, which is 1/2 because those 2's will cancel out. A3, that's 3 factorial over 3 to the 3rd. That's 1 times 2 times 3 over 3 times 3 times 3, which is 2/9. Right? All right, so AN, to write it out maybe in a more expanded form, wouldn't that be 1 times 2 times 3 up to n over n times n times n, where you'd have the same number of factors, which is n, you'd have n factors in the numerator and in the denominator, right? All right, so if I think of this product as a sub n equals 1 over n times 2 times 3 times 4 and so on up to n over n times n times n and so on up to n. Because n is increasing, the factors in here are at most equal to 1. That'll equal 1, right? That last term will equal 1, but everything other than that will be less than 1. What happens when you multiply a product, when you take a product of two numbers that are less than 1? Just generally, do you get is the product a larger number than both those numbers or smaller than both those numbers? It's always smaller because it's less than 1, right? You're multiplying two numbers that are less than 1. So I can say that this product, at best, has to be less than or equal to 1 over n, doesn't it? That's the biggest it could possibly be, and it will only be that for basically the second term, or the first term, I should say. But that product, is it ever going to be negative? Is this whole product ever going to be negative? So it's always also going to be greater than 0, right? So I can make the statement that a sub n has to be between 0 and 1 over n for all n greater than or equal to 1. And now I can say, well, then the limit as n goes to infinity, and just take the limit of all three of those sequences. Well, for 0, what's 0 going to approach as n approaches infinity? It's a constant, so it approaches 0. A sub n is what we're trying to figure out. So I'll just label it as the limit as n approaches infinity of a sub n. And then what does 1 over n approach as n approaches infinity? So what I've proven there is that the limit as n approaches infinity for a sub n has to be somewhere between 0 and 0. So not a lot of room there, right? So what does it have to be? So the limit as n approaches infinity of a sub n is 0 by what? Squeeze theorem. And again, I just want to go back to why. Because we're multiplying 1 over n by something that's always going to be less than 1. So it's always going to make, the product is always going to be smaller than 1 over n. Because 1 over n times something less than 1, it's always going to give you something less than 1 over n, right? All right. Let's stop there. That's a lot, and we have to do induction. So we'll do induction next time, and we'll finish up